like recording this gonna be. First, after we did talk about, I would say, electricity and magnetism. Now we are going to talk about the relation between the two. And this is going to be the electromagnetic induction. First, we are going to look at how Faraday's law relates the induced EMF in a loop to the change in magnetic flux through the loop. Then here I'm going to talk about what is called induced EMF. Induced EMF, from the name, it is looking at something that is not actual. It's not an actual battery or a source. And we are going to look at how we are going to talk about this induced EMF. How to determine the direction of an induced EMF, and we are going to study this in details. Most of our applications here, they are going to be talking about this. Now, what gonna cause what is going to cause actually this kind of EMF? It is actually we are going to talk about the changing in the flux, which will generate a circulating electric field. We are going to talk about the 4 fundamental equations that completely describe electricity and magnetism, and also we are going to maybe talk something about superconductors. Everybody is familiar with credit cards and the strip that we have on these, like that black or gray strip that we have on the back of the credit card, like this one here. We call it the card reader, and that is really sensing the information that is coded, like your name, maybe your social security, like all your identifications in a magnetic pattern on the back of the card. Therefore, this is going to identify whose card is this. Why must you remove the card quickly rather than hold it motionless in the card reader's slot? And we are going to talk about when we're going to have motion and different when we don't have motion. Energy convergence makes use of electromagnetic induction, and today mainly we will talk about Faraday's laws and Lenz's law to tell us about induced current. Also, we are going to introduce Maxwell equations and describe the behavior of the electric field and magnetic field in any situation. There is an experiment here that was, done by also, I will say, by different scientists, like during the 1830s. And these are really, all of them, they are central about the idea of that a magnet can introduce an induced EMF in a coil. And here you can see that there is that coil here, the yellow. It is connected to a galvanometer, and the galvanometer is a meter just that is gonna, I will say, detect small currents. And then when that magnet is brought towards the coil or removed away, then we are going to get that meter is going to move. When the nearby magnet is stationary, the meter shows no current. And here we can see again that we have now the North Pole is facing the coil, and we will see that there is going to be an induced current because there is motion. We are trying now to move the magnet toward from the toward the coil, or moving it away. We are going to find that the galvanometer is going to show a like kind of induced current, and that is really is produced by an induced EMF. Another experiment that is really important, we replace here the magnet with a second coil that is connected to a battery, like this one on the top. And then when we move the second coil toward or away from the first, there is a current in the first coil, but only when one coil is moving relative to the other. Also here, another experiment that is just here we have a switch, you can see here, and then we have two coil setups from the previous, and we keep the coils stationary, but we are going to open or close the switch. Then we will have the induced current occurring again because the current in the second coil is changing. Here also we have a coil in a magnetic field, and when the magnetic field is constant and the shape of the coil do not change, no current is induced in the galvanometer, you can see. And then a current is induced only when these factors change. Then here, what is really changing whenever we having like a coil moving in a in a magnetic field, or when there is a change in we'll say the magnetic field itself. In order to understand this, we are going to understand or go back to the idea of the flux, and we are going to define the magnetic flux by having that surface here divided into small areas. We call the each one dA, and then we can define the magnetic flux through the area element here to be d phi b as b perpendicular times dA. Here, the maximum magnetic flux through a surface occurs when the surface is face onto the magnetic field, because remember here we have area, the area vector, it is perpendicular to the area. Then when they are the magnetic field and the area vector are in the same, I would say, direction, then the angle between them is 0, and then cosine 0 is 1. Therefore the flux, which is defined BA cosine 0, is going to be simply BA. If the surface, it has some angle relative to the magnetic field, then the magnetic flux is gonna be between 0 and BA, depending on how much cosine is. When the surface is edge onto the magnetic field, which means the vector area, the area vector is perpendicular to the magnetic field, then here we are going to have cosine 90, and cosine 90 is 0. Therefore, the flux is going to be 0. Faraday was able to relate the, I will say, that flux, that changes in flux to, to the induced EMF, and we call this Faraday's law of induction. And he said when the magnetic flux through a single closed loop changes with time, there is an induced EMF that can derive a current inside the loop or around the loop, and that EMF has to do with the change in the magnetic flux. Then EMF equals negative d theta b over delta t, equals the negative of the time rate of change of magnetic flux through the loop, and we are going to understand why we have this negative. Now, the unit for the magnetic flux, it is Weber. And we know that Tesla times meter squared equals 1 Weber, or 1 volt equal 1 Weber over second. Now, in order for us to find out the direction of the induced EMF, we need first to define a positive direction for the vector area A. Then we're going to define area where it is located, like the area vector, and then we are going to determine the sign of the magnetic flux and its rate of change using the direction of A and B. And how we are going to do that, we are going to determine the sign of the induced EMF based on the value of the flux. Then if the flux is increasing, so delta theta B over delta T is greater than 0, and then the current induced is going to be negative. If the flux is decreasing, then d theta B over delta T is less than 0, then the induced current or EMF is going to be positive. Then here just I want you to know that it's going to be like kind of opposite. Then if it is greater than 0, the change in the flux is positive, then the induced current is going to negative. And then when the rate of the change in the flux is going to be less than 0, then the induced current or EMF is going to be positive. After that, we are going to use the right-hand rule to determine the direction of the induced EMF or current. We're going to curl the fingers of our right hand around the vector A and with our right thumb in the direction of A. And then if the induced EMF or current is positive, it is in the same direction as your curved finger. If it is if the induced EMF current is negative, then it is in the opposite direction. I'm gonna apply these rules here. And then look here, we have the vector A. It is actually pointing up here. And then I will be able to find that my thumb is going to point in the direction of A. And then what I will do is I will say B here is increasing, then the flux is going to be theta B greater than 0. And also it is becoming more positive, then d theta B over delta T is going to be 0, greater than 0. Then the induced should be negative. And when the induced or the current is going to be negative, what we are going to say, then the induced EMF is going to be, if it is positive, then the induced EMF current is going to be in the same direction as your curved fingers. And then we are going to find that the current here, or like the EMF, is going to be clockwise. Here, the second example here, the flux is positive, but it is becoming less positive, which means it is the d theta B divided by delta T is less than 0. And then the induced EMF should be positive. And when it is positive, then we are going to have the current here. We are going to have the EMF in the counterclockwise direction. Here we have the flux is negative, okay, because it's on the other side and becoming more negative. This means that induced EMF should be greater than 0 and then is going to be counterclockwise. The last example here, that it is less than 0, theta B is less than 0, and it is becoming less negative. then the induced EMF should be less than 0, which means clockwise. I'm gonna stop here and then post another video. Thank you.